Hello, I am Esra Ayaz. I will explain the project circuit that I made with my group mate Üzeyir Yaman from beginning to end. First, I will start by explaining the first task of the project, the 1-bit generator part. As can be seen, we set up this part on the first breadboard. The circuit where the blue LED is on above is the A0 circuit. This circuit produces a square wave with a frequency of 1 Hz. The circuit where the red LED is on below is the A1 circuit. This circuit also produces a square wave with a frequency of 2 Hz. The patch frequency of the LEDs is already understood. Now, I now we connect the outputs of both of these circuits of the oscilloscope probes and examine their graphs on the oscilloscope. The graph is as seen. The yellow graph above is the graph of the A1 circuit. In other words, it is graph of the one that produces a frequency of 2 Hz. The blue graph below is the graph of the A0 circuit. This is the one of the frequency of 1 Hz. The values are also written on the screen. Now secondly, I will explain the second task of the project to the 2x2 multiplexer circuit. We set up this circuit with transistors. Before setting up this circuit, we used the K-maps that were also included in final report. In these K-maps, we obtained the Boolean expressions for B0 and B1. Then we obtained the simplest from these expressions. Then according to these Boolean expressions, we set up multiplexer circuit as seen. We used BS 117 NMOS and BS 250 PMOS while setting up the multiplexer, while the green LED seen in the video shows the B1 output. The yellow LED shows the B0 output. Now, as you change the switch, the frequency of the LEDs also changes, as you can see. For example, the switch I am touching right now is the SM1 switch. This controls the B0 output, that is the yellow LED. When I open the switch, the B0 LED lights up with a frequency of 2 Hz. When I close it, it lights up at 1 Hz. The switch just below it controls the B1 output, that is the green LED. When I open the switch, the LED lights up at 2 Hz. When I close it, it lights up at 1 Hz. Now let's see the situation on the oscilloscope. As you can see now, there are graphs on the oscilloscope. The upper graph, the yellow graph, shows the B1 graph. The lower blue graph shows the B0 graph. Right now, when you can change SM1 switch, the B0 graph change. When I open the switch, B0 started to give a graph at a frequency of 2 Hz. When I close the switch, it dropped to 1 Hz again. As you can see, when I do same for the switch SM0 switch, the B1, the yellow graph will change. The switch is currently closed, and as you can see, it gives a graph at 1 Hz. When I open the switch, the graphs became at a frequency of 2 Hz. Finally, we connected the B1 output to the counter and B0 output to the duty cycle controller, to the relevant places in the duty cycle controller. And we moved on to the next stage. Now I will explain the first part of the third task of the project, the switchable counter circuit. In this part we made it using 74HC74 D-type flip-flop integrated circuits, logic gate in integrated circuits, decoders and display. As you can see now, the counter is counted one by one. We positioned the SC switch here. Since the switch is closed, the counter is counting one by one. When we open the switch, it counts by 2 as seen. When we close the switch again, it counts by 1. When we open it again, it counts by 2. As you can see, I am changing the switch. That's all. Finally, I will explain the second part of the third task of the project, the duty cycle controller. In this part, as seen, one potentiometer, one NE 5532 op-amp integrated circuit, resistors and capacitors are used. In this circuit, the duty cycle changes as the potentiometer is changed. Now let's see this situation on the oscilloscope. Right now we see the duty cycle change on the screen as the potentiometer is changed. When I am change the potentiometer, duty cycle also changed, as you can see on display. Thank you for watching and listening so much. Thank you.